Good morning. In the previous lecture, we discussed about histogram manipulation as well as what do we mean by spatial frequencies. Okay, so briefly discussing about the concept of spatial frequencies. So they are high spatial frequencies categorized into two parts: high spatial frequencies and low spatial frequencies. Okay, and from the given image. They are determined on the basis of how frequently the scene that is changing. Okay, like in this image, you can see that the first one is the image. It's aerial photograph. It is captured from urban area, while the second one is a very big grassland where we have a uniform kind of object. So in the first case, as the variation in the scene is very frequent along a particular direction or along all the directions. Okay, so in the first case, the high spatial frequencies are dominant, while in the second case, low spatial frequencies are dominant. So there is a correlation between on the basis of just seeing the details in the image. Okay, in terms of spatial variability, you can say that if spatial variability is very high, okay, in that case, the high frequency components are dominant. And if the image is more homogeneous in nature, it means uniform kind of object is present there. So in that case, low spatial frequency components are dominant. So there is a direct correlation between how we can able to determine whether the low spatial frequencies or high spatial frequencies, which one is contributing more to define a particular scene. Okay. So in this context, like spatial frequencies, presence of spatial frequencies, we are interested in to highlight certain details. So we have two types of filters. The first one is low pass filters and second one is high pass filter. Okay. In the first case, we just permit to retain in the image low spatial frequency details, while through low pass filtering, we block the high frequency detail. Okay, what does this mean? We want to smooth the image. So in this case, as you see, we permit low spatial frequency to pass. Okay, it means just we want to preserve the homogeneous details. We are not interested in sharp changes in the image. Okay, just de-emphasize very sharp changes, and we want to emphasize the homogeneous areas. If this is our aim, okay, then we need to select low pass filters. So in this case, low pass filter, like when you process an image using low pass filter and you generate output image, when you do the further analysis of spatial frequencies, presence of spatial frequencies in the output image, there you will see that that amplitude I talked about. Let's say if image is represented by function f, so this can be splitted into various sinusoids. Let's say I is equal to 1, 2 is equal to I is equal to certain very high value. It can be I can be taken infinite. Okay, and then after that we have a AI sine omega it. Yeah, omega I can be written 2 pi. Okay. So in this case, what happened? So a very large sinusoids are combined. to permit low spatial frequencies, it means the if in the output image if you analyze, so this AI value corresponding to the Fi small, for small frequencies the AI value is large. Okay, when you keep on increasing this frequency Fi, what will happen? The amplitude will decrease. It means the contribution of high spatial frequencies are diminished. Okay, and this will happen when you apply low pass filter. Okay, contributions, the amplitude AI corresponding to high frequency, high spatial frequencies are diminished through this process. Okay, here infinite, it could be, let's say, some value n. Better to take some value n. It can be n tends to infinite based on the transform we are using over here. So now the reverse happens in case of high pass filters. In using high pass filter, if the frequency is low, all the components corresponding to low frequency, the AI value decreases. Okay, while the high frequency details are emphasized. So if it is large, for that case, the amplitude that will be generated, that amplitude will be increased. So we emphasize the high frequency details, while the homogeneous areas which are there in the image, they are de-emphasized. Okay. So through this analysis, we have done correlation between while low pass filtering, what do we mean by suppressing the low frequency? So in low pass, allowing the low frequency and suppressing the high frequency. Meaning is that their amplitude is affected overall. If amplitude is affected, then just see in this case, what will happen? Very low amplitude, it's like very small. It's close to mean value. So it is not much contributing because this amplitude is very low. Okay. Overall, by using the high pass filter, what will happen once you generate the outcome? This will emphasize the edges present in the image. Edges are defined as a transition line from one object to another object. Okay. So applying low pass filter, high and medium frequencies are finally affected. They are filtered out. Okay. And image is resulted into the smooth appearance after the low pass filter. Because see, high and medium frequencies represent the sharp changes in the image. And if you decrease their effect in terms of if you decrease their amplitude, so ultimately the changes, sharp changes appearance will diminish. And that finally lead to the smooth appearance of image. So the way we visualize the image after the processing, and we say that, okay, now the appearance of image becomes smooth. It means it is also called as image smoothing. Okay, sometimes low pass filter is called as smoothing filter. One problem we have when we process the image, due to the smoothing operation, uh, many interesting features will be lost. Okay, because while the smoothing we are suppressing the edges. Similarly, if there are many features that we want to keep in the image while performing maintaining the smoothing operation, but they are lost. So this is the reason why we want to go with the smoothing operation with edge preserving preserving the edges. So we require a smoothing filter, okay, that highlight the homogeneous features in the image. At the same time, it should also preserve the edges present in the image. We'll see. We have these kind of filters as well. In high pass filters, after applying a high pass filter in the image, the abrupt changes that we call edges, okay, they are preserved. And this is presented by steep gradient in distal DN values. We'll see it. So boundaries which are there in the image, they are called as edges, because at the boundaries we can see, if you move across it, you can see the difference in distal numbers. Okay, so they occupy only small area in the image, thus high frequency features. The sharp changes lead to the high spatial frequencies, dominance of high spatial frequencies. Their amplitude A is high in that case. High pass filters are designated to emphasize high frequencies and to suppress low frequencies. We have already seen it earlier. Applying a high pass filter has effect on of enhancing the edges. See, if you see this first image, edges can be at the road boundaries. It can be the outline of the building roof. Okay. When you applied the high pass filter, that edges is further enhanced. Further enhancement in edges means if you move across the edge, in the original image, let's say there is a difference delta. It can be, let's say, we have edge. These are the two neighboring pixels. In this case, let's say the distal number is 45 while 135. So if you move in horizontal direction, so delta is it is representing difference. It's 135 minus 45. It comes out to be 90. Okay. What happens when you apply high pass filter? This 90 will increase. Means the delta value that we talk, the difference, this will increase. Okay. If this is increased means the contrast that you see, the difference is further enhanced. Okay. So this is the reason why we call it edge enhancement filters. Okay. So we have two types of high pass filters. They are gradient directional filters, or they are non-directional. We'll call them Laplacian filters. So we start discussing filters with the basic concept of convolution. Okay, and the concept of array. What we do, as this is called as local operation. Who will tell me what do we mean by local operation?
Sir, it will work nearby the pixels, like surrounding pixels.
Okay, good. Um, any other student?
Same, sir. If you select a pixel for any operation, it will work on the surrounding pixels also.
Okay. So for image improvement in terms of visual quality, we discussed about two operations. The first one is point operation. Okay. And the second one is local operation. What we do in point operation, let's say we have already discussed in case of histogram manipulation. This is a function to which we pass dn input. Okay. And we generate dn output. And this is at the location. Let's say if this is, we define it by j. So at a time, the j at jth location, the input is selected, and at the same jth location, it is replaced by the output. Okay. So in this function, the input is only the seed pixel that is selected. Fine. And we have seen it in histogram manipulation. Yeah, contrast stretching. One assignment I have given to you in the laboratory. There are 3 problems and you need to solve that. So histogram manipulation and contrast stretching, we consider only seed pixel and it will be given as input in the linear and non-linear function f. F is linear, we have a linear operator, non-linear, logarithmic and exponential we have discussed. And finally output is generated. Is it clear? Now in local operation, in the local operation, Tn output at jth pixel is generated by the function of Tn input at jth location and other Dn input if I write it's j plus plus, or you can also write jn input j plus plus, it goes towards positive x and positive y both. Okay, while dni it will go j minus means towards lower side, means either minus x or minus y. If let's say image, in this case, this is x and y, it is defined over here. Okay, so plus j, if this is the pixel. Okay, so j plus plus means we are talking about these directions, and this minus means just before that. Okay, now at what extent we can move, like when we are going to consider the surrounding pixel to the seed pixel as a part of input. So how many surrounding pixels we can consider, and what is a way to consider them? For more simplicity, I can explain it through the block diagram. First, what are the surrounding pixels? Let's say this is d I comma j. Okay, and we have defined the I is toward x and j is toward y. This is y and this is x. So d and I comma j is selected as a seed pixel. What is surrounding? Surrounding will be towards I. This can be the surrounding pixel plus y and diagonal. We can say this is 3 cross 3. Can we have surrounding 4 cross 4? No. If you further add, it will be 5 cross 5. So we define surrounding always in the odd numbers. They are not even numbers. Okay. 5 cross 5, then it will be 7 cross 7. So the surrounding pixels which are there in the surrounding of seed pixel, they are within 3 cross 3 dimension, where the center is D and I J seed pixel, or 5 cross 5 or 7 cross 7. Okay. Now what we do, using all these, they are processed through a particular function f. Okay. And by processing to this function, dn output is generated. Okay. And this dn output is further used to replace this seed value. Now we need to define what are the functions. What are the functions available which are used to use the seed pixel value and surrounding pixel value, process it to generate dn output. Okay. Surrounding we have defined. Surrounding can be 3 cross 3, 5 cross 5, and 7 cross 7. Okay. It means while defining the function f, 3 cross 3 can be taken, 5 cross 5, and 7 cross 7 can be taken. Is it clear? Now this function f that we define, it is called as kernel, or it is 3 cross 3 array. What we do to define function f, we provide weight to all these cells. To that weight, we multiply the actual dn number and we generate dn output. Okay. So this function is defined in the surrounding of dn input. Okay. If it is 3 cross 3, the kernel will be 3 cross 3. If we are interested in 5 cross 5, 5 cross 5. Similarly, the large odd numbered array can be generated. Okay. Now, how it looks like once you, the function f that we want to keep over here. We'll see too. If we are interested in surrounding 3 cross 3, then this is function f. Okay. So entire it will be. How it is there? We define the kernel. We also call it structuring element. We are interested in 3 cross 3. Then weights are given. RST till Z These values are coefficients of filter. This filter represent function f over here. So these values are the coefficients. And what we do, these filters are used as a window, and they slide over the image. Okay. So this the filter is slided over the image, and let's say if it is there at a particular location, how it generate a DN output. So the output that is generated, it is written over E processed. Okay. So it is just overlaying over the image coefficients. They are multiplied by the corresponding digital number. V is multiplied by E, R is multiplied by A. If you put over here, if you overlap this filter over this image, so R is the coefficient and it is coming over the pixel A. So you multiply it. Similarly, U, it is coming over D. You multiply it. Okay. And after that, you need to sum it up to generate the output image. This process is called as convolution. So this function f that we are using, it is called as convolution function. Is this process is linear or non-linear? The convolution operation that that is performed over here, it is non-linear function or linear function? Ruchi Dwivedi, could you please unmute?
Yes, sir. Hello.
Yeah, tell me, this convolution operation is linear operation or non-linear operation?
Sir, it's linear operation.
Why it is linear operation?
I don't know, sir.
Okay, please mute. Who will tell me why it is linear operation? You need to think about it. This is for the homework.
Sir, there is no higher power. Higher power is multiplied. Only power 1 is multiplied to each.
Yeah, correct. Because we are just summing up the two multiplicating factors. So after multiplying two values, we are summing them up. And in the multiplication, we don't have power of 2. So all elements have power of 1. Okay. So this is the linear operation. One example is given over here. How we now see the kernel which is used over here. That kernel has certain coefficients. Okay. On the basis of type of filter, like whether we want to use it as low pass or high pass, we need to provide values to these coefficients. Okay, so high pass filtering and low pass filtering, to this process are categorized as a convolution operation. It is linear operation. Okay, and on the basis of requirement, whether we want to process the image using low pass or high pass, the values to these coefficients are given. One example is discussed over here. For all the entries, the values are given 1/9. In this case, it starts from R to Z. Value is given 1/9. Okay. How we perform the convolution over here? You need to multiply it like as in this case, the fxi comma yi. In this way, it is defined along x-axis. Index I we put, along y index j. Okay. So let's say the location of this pixel, location of here the pixel is selected E. For E pixel, if we define location by I comma j, okay, I comma j indicate location of pixel E. Then at location xi comma yi, the distal number value is given by fxi comma yi. So it can be written as dn I comma j. So what we write, that dn output is equal to summation of weighting function, again comma j into dn I comma j divided by summation of wi comma j. I've just rewritten this equation using the symbols we are considering over here in the previous case. Okay, so wi comma j, along this we have I. Okay, this is j. Fine. So dni comma j, similarly I comma j over here. And so when we provide these coefficient values to the kernel entries, so they are square or rectangular window containing coefficients or weights. Okay. Mostly the size of window will be odd. Okay. Generally, we define surrounding to the seed pixel in odd numbers. Okay, odd number of pixels, including the seed pixel. Whether they are 9, then they can be 25. Okay. In convolution, kernel moves over the entire image. Starting from I comma j, kernel, we just move over the image, the entire kernel. Okay, to generate the output image. In this case, different set of values for coefficients are given. Okay. The first column, we have -1, -2, 1. Second column, all element 0, while third column 1, 2, 1. keeping in mind, if you add them, the total value is 0. Okay. For a 3x3 image, this operator is applied. Okay. And the value is generated. It is coming out negative -63. But what is the effect? 147, it is coming -63. It means by this operation, we are just decreasing 147 to -63. Okay. Here 205, 147. So 147 is not elevated close to 205. It is further decreased to -63. It means somewhere here and even at this location, mainly this location, what we are doing, we are enhancing the difference. If we are enhancing the difference, it means we are highlighting the edges. So this filter is called as high pass filter. You have if structuring elements, the coefficients, they are chosen in this fashion. So it is a high pass filter. Okay. Similarly, using all coefficients values 1/9.
Sir,
Yeah.
in previous example, can we explain it like that? Ki we are suppressing the lowest value. That's why it is also the high pass filter.
Oh, no, so suppressing what lowest value
The
means? You are talking about DN value.
yes, the lowest value like in that matrix, the 147 is the lowest pixel value. So we are suppressing it to -63. So we are suppressing the lowest value. That's why it is also the high pass filter.
I will come to this discussion. In high pass filter, what we do, not only suppressing, we are just enhancing the difference.
Yeah, yes,
So
sir. We are enhancing difference by suppressing the. Can we explain like that? I am just asking that.
see,
Is
we
it the
can
right explanation?
no. So we explain it like that. In consideration with the surrounding pixels, okay, the
Yes.
seed pixel value is either enhanced, either increased or decreased, considering the increase in differences to the surrounding pixels.
Okay.
Got it?
Yes, sir.
Because if
Thank
let's say surrounding pixels have very high values, okay,
yes.
in that case, what will do? Seed pixel value will decrease, so the difference enhance. If the surrounding pixels have very low value, then the seed pixel value increase, keeping in mind, keeping in consideration to increase the differences of a
Yes, sir.
seed with the surrounding.
Okay, sir. Yes.
Got
Thank
it?
you.
हाँ,
Yes.
you're welcome. क्योंकि यहाँ पे क्या है कि the surrounding pixels values are more than 149. Okay, and it is 147. So what we do, if we further increase it, then it will be close to 221, 198 like that. It is not a case. To increase the difference from the surrounding pixels, what we do, we decrease it. Okay, if the coefficient of the kernel, if they are considered same, okay, so 1/9 is given for all the locations, and if it is used to process 3x3 image, so the DN values are given. Just see over here, nearly all the values are 106. Mostly if you analyze it, so mostly the values are around 96. 98 we have 99, 95, 98. Okay, 104 and 100. One value we have 108, but all the values uh, 7 values are less than 106. Only one value is more than 106. Okay. After applying this kernel where all the coefficients are same, they are having value 1 by 9. Okay. Then the value is generated 98. What is happening over here? 106 is decreased in such a way that its value become similar to the neighboring pixels. If all the coefficient values are same, and by using that kernel if image is processed, so what is overall happening in the image? The seed pixel that is processed, so it is processed in a way that its value either decrease or increase to match the values of surrounding pixels. This happens. Okay. And this is called as smoothing the detail. If somehow the difference is large, by using averaging filter, the difference between seed pixel and surrounding pixel delta decreases. And it all depends how we are selecting the coefficients. Okay. How the kernel coefficients are selected, on the basis of that, the operation is performed. So there are overall using these, the first set we discussed this one, and this is the second set of kernel. In these two cases, what we have seen, after processing the image through filter, either the central seed pixel value becomes close to the surrounding values, or seed pixel value becomes different than the surrounding values. Only these two effect will appear in the processed image. So when just see when this seed pixel is processed, and after the processing, its value becomes similar to the surrounding pixels. What does this mean? We are suppressing the high frequency detail because we are suppressing the edges. We are suppressing the variability in the scene by this filter. If we are suppressing the variability exists in terms of delta, that is a difference between two pixels. If you move along the line and you can notice a significant delta, it means there is a variability in the scene. Delta means, let's say, dni minus dni plus along a specific, if you take mod, this is delta. Okay, so moving along the line, you can notice a significant value of delta. Okay, at a definite interval. Let's say if you move along the line, here you can change sufficient delta. Here 4 and 5 location, you can notice the significant value for delta. It means at all those locations, edges are present. By this operation, what is happening? Edges are present means this difference. What happens over here? The 99 minus 106. Now 106 minus 98. Okay. There is a difference of around 7 and 8. After the low pass filtering, it comes out to be 98. Now difference is 0.33 and 0.77. Okay, so what you are doing, you are decreasing delta. Scene variability details are losing. It means The frequency, high frequencies, Fi, corresponding to high frequency, the amplitude AI is decreased. Okay. So what we call, on the basis of output and spatial frequency analysis, this comes into the category of low pass filter. Okay. And earlier we have already defined that low pass filter is also called as smoothing filter. Okay. Just see over here what happens. This is the low value corresponding to the surrounding pixels. So low value surrounded by high values. After low pass filter, if we have this type of kernel, 100 its value is elevated to 191. If high value surrounded by low values like 125, it will further decrease to match the surrounding pixel 65. And just see in this image, this is the input image. Okay. And this is processed by considering a different neighborhood. Okay. First 3x3 neighborhood, then 5x5, 9x9, like that. And just see how the smoothing occurs. Image is blurred and the level of blurring is highest in case of largest size of kernel. If you select kernel 35x35, that is the last image, just see it's blurred. Okay. Why it is so? Because you are considering very large surrounding to replace the seed pixel value. Okay. So the details which are there in terms of transition, in terms of difference in digital numbers from transition in a transit from one pixel to another pixel, that difference will be decreased. Just see in the image. See where the sharp changes you can notice over here, that sharp changes are diminished and uniform details are highlighted. What is problem over here? There are many important details which are lost. Important details means there are certain important edges. They are very small. If there is very small object, so that is small object boundaries are mixed with the surrounding object. So you can't differentiate. Okay, what is the exterior boundary of that small object? So in order to preserve the edges are very important features. We need to go with weighted averaging. So in weighted averaging, what we do, the weight of seed pixel value is highest compared to the weight we assign to the surrounding pixels. So the diagonal, we have a list weight highest to this, and then we have a weight to horizontal and vertical coefficients. So this is more effective smoothing filters, and it can be generated by allowing different pixels in the neighborhood, different weights in the averaging function. So pixels which are closer to the seed pixel or central pixel, they are given more important compared to uh, the kernel blocks which are away from the central pixel. In this example, you can see that after applying the smoothing filter, what happens in the visual quality of image. The first one is original image. It is smooth to eliminate very small detail. You can see many dots in the original image. Those dots are removed in the smooth image, and then after that binary thresholding is performed. What will be the histogram in this case? If you generate the histogram, and this is 8-bit grayscale image, so 0 to 255 we have. So you can notice it's a bimodal histogram. Okay. Somewhere here you can define the threshold, above which provide 1, and below this provide 0. So 0 to DN threshold, after binary thresholding they are given 0, and 1 they are given 1. So in thresholded image you can see the large white blobs which are present in the input image are highlighted, while very fine and small area blobs, they are eliminated. Take 5 minutes time to make note on the discussion which we have. Then again we resume our session after 12:07. Okay, so we have seen how averaging filter work, but the disadvantage that we notice is to it blur the edges and other sharp details. So if you want to preserve the edges and other details, but at the same time, we want to highlight the homogeneous areas, then we need to go with median filter. Okay. So this median filter retain edges and sharp details while removing the noise. And you can see in this image. So in this image, it's noisy. Okay. By using the averaging filter, what happens? That noises are removed, but at the same time, these are the called edges. Okay. So this is a printed circuit board PCB where the sharp details or edges are diminished up to certain extent. But when we operate median filter, what happens? All these noise components are removed while the edges, while preserving the edges. Okay. So median filter filtering often used to remove noises from the image. This is low pass filtering, LPF. Okay. And smoothing, sometime median filter works better than averaging filter, as you see in this case. How this median filter operate? All the 9 elements, you arrange them either increasing or decreasing order. Like when you overlap, this is 3x3 image. Okay, if you overlap the median filter, all the elements are arranged in either decreasing or increasing order, and their median value is used to replace the central value. Okay, so this is not a convolution operator. In the convolution operator, what we do, we multiply the coefficients to the corresponding distal numbers and we summed up. While in this case, we arrange the numbers, DN numbers in increasing order or decreasing order, and the median value is used to replace this. Okay, this is another example where the first one is the original image. Deliberately, noises are added and they are further filtered out using median filter and convolutional low pass filter. So this is the averaging filter, as you can see over here. But what happened? Just see these sharp details, these edges. This is the edge and it is de-emphasized. And even just see these edges, all these edges are de-emphasized. While in the median filter, the noises are removed at the same time, the edges are preserved. Now we see another example of high pass filter where the coefficients are chosen at the central pixel location. It is 16, while surrounding locations, the coefficients are -1. What happens after applying this kernel? If you apply this kernel over the image, then low value surrounded by high values. This is low value surrounded by high values. What happened? It will further decrease. What is objective? To increase this delta. Delta is the difference between dni minus dni plus 1. This is equal to delta, and this will increase as you see in this case. If you move along this line, 201 minus 120, if you move diagonal, it's delta. If you vertical, it's delta. So there are three major directions where we analyze the changes in the distal number: vertical direction, horizontal, and diagonal. Along all the directions, you can see that 39 is decreased from 120 and the difference from 204, 104 and 200, the difference delta is increased. And if there is a high value surrounded by lower values, then what happened? It will further increase to increase the difference between central pixel and surrounding pixels. So this is also called as high pass filter, the way it operates over the image. And this is an example of high pass filtering. This image, grayscale image, is captured from the urban landscape, where you can see these are the exterior boundary of buildings. Okay. So what you will get in the image, you will get only edges. And the homogeneous areas are suppressed. You can't notice the homogeneous areas, but edges are highlighted. There is a query like what will be the shape of histogram of filtered image? And the second problem is what will be the effect if 16, like in this previous case, if 16 is reduced to 8. In both cases, what will be if 16 is replaced by 8 in the previous kernel? Okay, you need to think about it. Now, like this is the histogram of original image. So the original image is equal to summation of low pass component and high pass component. Low pass component histogram is like this. Okay, while the high pass component histogram will be centered around 0. Okay, and the highest value we get at 0. Now we will discuss about edge detection and how it is done using high pass filter. A few cases we have already seen earlier. In the edge detection, the areas of low spatial frequencies are smoothed out, and the high frequency areas are retained. Then high frequency areas are also called as edges. So edge detection can be done subtracting an original image from a smooth image. Like original image is equal to summation of low pass plus high pass. Okay. What will happen? You perform the smoothing. If you perform the smoothing, what will happen? A high pass component will be eliminated. Low pass component will be left. If you further subtract output minus low pass component, what will be left? Left will be high pass component. So low pass is the smooth image, and this is input image. It's low pass process. If image is processed by low pass filtering, if that processed image is subtracted from input image, you will get the edges only. High pass, like high frequency components, they will be obtained by subtracting the original image from a smooth image. Edge can also be detected by spatial derivatives. Okay, and edge detection kernels, zero sum. Like if your value is 8, if you minus 1 and 8, if you add them, the value is 0. We call it zero sum. Even one example we also discussed earlier. In this case, this is also edge detection filter. If you sum them up, what will happen? You will get 0. All the coefficient summation is 0. So edge detection kernels, zero sum, they can be directional or they can be non-directional. That is Laplacian. Now see in this case, In this example, let's say at this location we have a difference. This is delta. Okay, this is in original image. If you smooth, what will happen? And this case, this is the labeled. Come over here. Okay. So in a smooth image, now this is the delta from this location to this, and then move to this. This is delta. So this delta decreases over here. And further, if you subtract smooth original smooth from smooth, you subtract to original image, you will get this. Okay. Now see further, this delta will. Here you can see the log change. This is again delta retained. This is delta dash, delta dash. You can, this is delta dash, delta dash. So delta dash is less than delta. In this image, you can see that the input image is equal to low pass component plus high pass component. So if input image low pass component is subtracted from input image, you will get high pass component, and it is seen over here. High pass component edges are highlighted, while just see the low details are in the homogeneous areas. All the details are not very evident. So by using 3x3 kernel, here we use 7x7 kernel. Just see the effect of blurring is blurring is more compared to 3x3. Okay. Now we have a special derivatives. Let's say this 2x2 kernel is selected, and by using it, we derivatives, how derivatives can be used to generate the edges. We take a horizontal first difference, that is, just take the difference of these two, a minus h. So this will emphasize the vertical edges. Take the a minus v, this will highlight the horizontal edges. Diagonal a and h, if you will take difference between them while processing, this will emphasize the diagonal edges. And these are the kernels which are used for highlighting the edges. So in the first derivative, this is vertical edge highlighted. Horizontal edge will be highlighted in this. Now the 2x2, it's row kernel and column kernel. Here 2x2 matrix we have. Similarly, we have azimuthal. Second derivative, row and column. Now we have, in this way we define the kernels where the diagonal elements are, diagonal edges are highlighted. Okay, and they can be written in terms of function. So f dash is the derivative of function f. Function f x comma y represent what is the distal number at location x comma y. And these are the examples by using a derivative. Okay. So just see in this case, vertical edges are highlighted. While in this case, you can notice horizontal edges are highlighted. Sorry, in this case, horizontal edges are highlighted, while in this case, diagonal edges, you can notice, just see, they are highlighted. Similarly, in this case, df by dx and df by dy. Okay. So if you take differences along this, and you can take difference along the x-axis. Okay. So this is again representing how the vertical and horizontal edges are highlighted by taking the first order difference along X and first order difference along Y. Now we have the third type of edge detection approach is edge detection kernel, that is zero sum. So sum of all values in the kernel, they are zero. In convolution, divide by 1, not 0. So produce zeros in the uniform areas. If you apply it, if let us the grass field, and the grass field is populated by, let's say, decimal number 130. But once you apply this zero sum filter, so in that case, all 130 pixels will be 0. Okay. So produce 0 in the uniform areas. We'll see it. Produce low values in low spatial frequency areas. And it will produce very high values in high spatial frequency areas. In this case, you can see linear edge detection kernels. This is the vertical and horizontal filter. Horizontal edges are highlighted. And then diagonal. This all elements. Summation is 0. Okay. And again diagonal. So this is example of vertical template convolution over here. In the original image, see the values are given 2, 2, 2, and 8. So edge we can notice here is the presence of edge. Okay. When you process it, uniform areas 0. At edges you will get 18. And just see the difference. 18 to 0 and 0 to 18. While here 2 to 8. So difference is 6 over here, while the difference is 18. And just see the thickness of edge is further increased. Now it is not 1 pixel thickness, it is 2 pixel thickness. Okay. So for this, we use a vertical template. So vertical edge is highlighted. This vertical is used and vertical edges is highlighted in this case. And by using this, the horizontal edges are highlighted. Diagonal edges are highlighted using these two. Okay, this is performed through the it's a convolution operation. Similarly, in this example, you can see that there is a change in the kernel coefficients. Now we have first column and third column -1, while the second column is 2. Okay. The same image is processed, but what we have a 8. Thick edge is there. 2 to 8 again equal, then again 2. By using this filter, what will happen? 0 to 18, again 0, then again. So it's 2 edges is highlighted over. First this edge is highlighted, then this edge is highlighted. So the linear edge is detected over here. It's a 2 pixel wide line, similar to this case, as we discussed over here. This is a 2 pixel vertical line. And in this case as well, this is 2 pixel vertical line. Okay. Now we have a non-directional edge detection. In the previous cases, we discussed the kernels which are directional in nature. We identify vertical edges, horizontal edges, and diagonal edges. We have the filters which are non-directional in nature. They can identify edges oriented in any direction. We call them Laplacian operator, and they are second order derivative. Okay, so double difference is taken for the fx comma y. Okay, so this non-directional edge detection filters are insensitive to directions. They produce edges in all direction. They suppress the uniformly varying regions, as in case of first derivative, and they are very sensitive to noise. So second order filters highlight the noise in the image. Okay, and this is one of the example. Okay, vertical and horizontal 1, diagonal 0, central -4, summation 0. And you can see when we apply the Laplacian filter, the edges are highlighted in all the directions. Now we need to determine how the edge strength and direction we compute. So edge strength is resultant value of edge detection filter, df by dx and df by dy. If you take a square root, it gives you vertical edges and horizontal edges. Using those two, we calculate the edge strength. Okay, and edge direction we can estimate by if you take this df by dy divided by df by dx. So we have certain first order filters like the Sobel filters. So this is an example of Sobel filter. -1, -2, 1, 0, 1, 2, 1. Okay, 1, 2, 1. The second row 0 and third row again -1, -2, -1, such that summation of all the coefficients is equal to 0. Similarly, this kernel will highlight the diagonal edges. Some other gradient of first order filters we have like Roberts, Prewitt, and they differ in terms of the values of coefficients. Now, the first one is the input image, and edge strength and edge direction is generated by using the formula given. The overall objective in the edge enhancement is to sharpen the edges in the image. It is done applying high pass filter in an image. So the add high pass filters image back to the original image. This produce the edge enhanced image. So there is a way. First, apply the high pass filter, and then high pass filter image. If you add it to the original image, the edge is further enhanced, and it is seen in this example. Third one is in image generated by adding the original image with the high pass filtered image. So we have discussed about how we can change the visual quality of image to interpret the details present in the image. We have discussed about histogram manipulation. Then after that, we discussed about what do we mean by spatial frequencies and how by changing the spatial frequencies, the details can be highlighted, noise can be removed. Okay, so the way we suppress low pass frequency or high pass frequency, we come up with the filters, low pass filter and high pass filter. Okay, low pass filters, we have seen that we have an averaging filter, we have median filter. In high pass filters, we have already discussed the first order derivative filters, second order derivatives. We also call it Laplacian. Okay. Then further, we determine the edge strength and edge direction. Okay. So various operators we have discussed. And there are certain questions given in the PPT. I expect you to go through those questions and see what could be the answer for that.